So our next speaker is Kristina Gulordava. Kristina is a postdoc in the Amore ERC project at Universitat Pompeu Fabra. Recently received her PhD from the University of Geneva, where she worked on computational syntax. Kristina works on grounded word reference in child acquisition using neural network models of language and vision. Thank you, Kristina.
Hi. Today we'll be talking about work that was published at NACL in collaboration with Piotr Bajnowski, Eduard Graf, Tal Linz, and Marco Baroni, which I did at internship at FAIR Paris. If you don't get the title of the talk right away, just wait. Oops, sorry. So I will be talking about recurrent neural networks. These models became a cornerstone of NLP. They were shown continuously to outperform previous models, for example, as part of sequence-to-sequence models for machine translation or dialogue, and also as part of as trained as language models, in particular bidirectional language models. And this kind of features extracted from these models were used to improve syntactic parsing, and most recently for contextualized word embeddings, ELMO. RNNs are sequential models, so they are natural models to model language, but they don't have any explicit structural representation. And this kind of representations are supposed to be part of the linguistic structure of the sentence, and as linguists think about it. So, for example, we know that there are some relations like subject or clause that exist in the sentence that help us process it, but RNNs don't have this kind of structure as part of their architecture. They also, especially if we train language models, RNN language models, when we do that, we don't actually use any kind of syntactic information. Normally, the objective is just predicting next word, like in this image, and so there is no incentive for the RNN to actually learn kind of abstract syntactic representation. On the other hand, the success and many tasks, like syntactic parsing and in general all language tasks, suggest that they do learn some syntax. So the question is, do the RNN language models actually learn kind of just surface patterns of language or more abstract syntactic representations? And to answer this question, Tal Linz and colleagues in 2016 proposed a task which is based on solving the subject-verb agreement in English. So if you have a sentence like, the dogs play in my neighbor's garden, bark. So we know that bark should be plural because dogs are plural. And you can actually test whether the model gets it correctly by comparing its probability of predicting bark, plural, versus barks, singular. So if it gets high probability for the correct form, we assume that the model has solved the agreement problem. And of course, this is a task sensitive to syntactic structure, because we know that bark should agree with dog in plurality because they have a subject relation. And this relation is local in the syntactic structure, but it is not local in the linear order of words. So if you just look at linear order, maybe we would say that garden or neighbor should agree with bark, but that's not the case. So one of the problems with the initial formulation of this task is that the RNN, even if it solves it correctly, can actually rely on some features which are not syntactic features. Maybe it just relies on lexical or collocation cues. Like, for example, it thinks, okay, so dogs are things that bark normally, so we need to actually align dogs and bark and not garden and bark. So it's kind of reasonable suggestion. So to kind of really probe recurrent neural networks for their syntactic abilities, we actually want to answer really like, what does it mean actually to learn syntax? And there we can go for inspiration to Chomsky, which famously coined this phrase, colorless green ideas sleep firstly. And he uses to basically show that, demonstrate that grammatical judgments are independent from semantics and language use. So when you see the sentence, maybe you see it first time, maybe you don't really understand what it means, it doesn't mean probably anything, but you can say, if you're English speakers, that it's a grammatical sentence. Well, for example, if you look at a very similar sentence, colorless green idea sleeps furiously, which just differs in one morphological change, you know that it's a ungrammatical sentence because there is no correct agreement there. So using this idea, we can actually really probe RNNs in their knowledge of syntax. Do they really learn abstract syntactic relations by just modifying the task and looking at the kind of sentence which doesn't make sense, but they are still grammatical. And we expect the model to guess correctly, if it learns syntax, the right form, plural or singular. So in this work, we evaluated RNNs on these colorless green sentences. We looked at the different agreement constructions, which we extracted automatically, and we also evaluated multiple languages with different morphological properties. And also, last but not least, we did a comparison with human performance. So these are just a couple of slides about how we extracted actually this kind of sentences. We used syntactically annotated corpora known as tree banks. So this corpora contain annotation for each sentence of each syntactic structure. So we can use that to identify the relations of agreement and see, find this kind of pairs of cues and target, where cue is preceding word and target is the word where we want to identify the right plurality. We also we extracted the complex constructions which require reasoning over longer context. So we have at least 3 tokens separating cue and target. So this is supposed to be harder for the model. And this is just kind of examples that we extracted. This is not only subject agreement, we had other constructions too in languages such as Russian, and we also had very long dependencies sometimes, like this example in Italian. So this is just statistics of the data we extracted, at least like between 2 and 20 constructions per language. English is the least morphologically rich, so we had fewer sentences. And so first we extracted natural language sentences containing interesting cue-target pairs of agreement. And what we did next, we just kind of generated colorless green sentences by substituting all content words with morphologically matching words. So the resulted sentences are grammatical, but they're now nonsensical. And we generated 9 sentences per 1 natural sentence. So our relation is as before, so we evaluate 2 target forms, plural and singular, by the probabilities, and if the correct form has high probabilities, we assume that the model guessed correctly. So this is our setup. The most important thing that we evaluated, the models I present are LSTMs, and they are trained on the Wikipedia text, which doesn't include at all the test set that we use. No nonsense sentences there, just normal text, and we optimized based on validation perplexity. So our models didn't observe at all these kind of colorless green sentences. And these are kind of baselines which allow us to see whether these models really require, to resolve this agreement, we really need longer context, and whether, for example, n-grams can actually do that even for non-sentences, just to control. So these are results. As you can see, first of all, LSTM outperforms other baselines, so we do need longer context at just 5 grams, and we do need some kind of generalization ability. And what is most striking, and we didn't actually expect, that LSTMs are really good also at non-sentences. So you can see that the difference between red and green columns are relatively small. So it means that they actually get agreement also in these nonsensical sentences. Finally, we evaluated also human performance to compare these results, to put some kind of upper bound. And we did it on Italian, and we basically asked the people to do the same task as the models, that is, choose between singular and the plural. So this is the results. You can see that people are better than the model a bit, but what is interesting is that they also do more mistakes, make more mistakes in the case of non-sentences. And this gap between original and non-sentences is basically very similar between humans and LSTMs, which suggests that our models really do capture some syntax. So this is basically the conclusion, is that we showed that these models really capture hierarchical abstract relations, not just surface patterns based on, let's say, collocations or frequencies. And this kind of line of work was extended after our publications. There were many other people that showed very similar results on other type of constructions, even more complex constructions. Another interesting part of this work is that we can actually use this data. This kind of data is useful to analyze the models. For example, we found that LSTMs are much better at this task than simple RNNs. And so the question is, why they're better? How do they exactly encode this hierarchical information? And so you can use this kind of data to probe exactly the mechanism of LSTM.